Hi everyone. This video will be a bit different from what you are used to because we'll be reviewing a research paper that I think deserve more attention or already have a good attention, but it's still in the context of a distributed training. And the exception is we have the guest of the author of the paper as well reviewing the paper. So hopefully it will answer a question that usually you don't have when you read the paper by yourself. So this is Arthur Douillard, and I let yourself introduce.
Thanks. So, hello everyone. My name is Arthur Douillard. So, I'm a research scientist in DeepMind in London, and I've been working for now 2 years on distributed learning across many variants of DiLoCo and DeepACO. So that's kind of my thing right now. And here I'm showing the latest paper of DiLoCo, which is named Streaming DiLoCo.
Okay, okay. So I think we go through the paper one by one, and if we have question, a bit like a discussion, and we will see. So I'll start with the abstract. So training of large models is typically distributed across a large number of accelerators to reduce training time. Apart to reaction. So yeah, so I think we have to introduce a bit what is DiLoCo before streaming DiLoCo. Maybe you want to talk about
Yep.
it first.
Yeah, absolutely. So there is many ways to distribute your networks. So by
Mhm.
distributing, I mean like when you use more than one device, so more than one GPU, more than one TPU, you need to distribute your training across multiple devices. So this is required now for any kind of large-scale LLM because you will have a model that is so big it cannot fit on a single device. You'll have so much data you cannot put everything in a single device. So you have many methods. You have
Mhm.
methods to distribute your model. So you have a tensor parallelism, pipeline parallelism, for example, that you can see probably other video with Picotron and Ferdinand. But you also have a method to distribute data, so data parallel. This is what I'm interested right now. Data parallel, basically, you have multiple replicas, so the same copy of the same model across multiple devices. Each copy is going to see a different subset of the data. They're going to do a forward, a backward, and then they're going to do a all reduce or the gradient to synchronize those replica. So they're tightly synchronized at every steps. So that's what everyone is doing, but it only works if all your devices are in the same location. So there's a co-location constraint, as highlighted by Ferdinand. The problem is like right now there's a lot of compute across the world, but the compute is not always in the same location. Just because some people have built a GPU on different location, because also you cannot have too much compute in a single data center because you have literally like electricity constraint where you cannot build more power plant at the same location and everything. So what if we could use like non-collocated compute across the world? That would be the dream. We can first here do it with data parallel. Later we can see tensor and pipeline parallel across the world. With data parallel, you cannot do it across the world because you synchronize at every steps. This synchronization is going to be very costly. So maybe you're going to wait like 5-10 seconds for every steps to synchronize, meaning during these 5-10 seconds, your GPU is not working at all, which is just wasted compute. And that's why, like in practice, doing data parallel across the world is not feasible. So that's kind of the goal right now of the DiLoCo family of algorithm.
Okay, so it's
Um,
enable training across different type of hardware. Basically, it could be a cluster, connecting cluster together, or different GPUs like AMD, NVIDIA GPUs together. Okay,
yeah.
interesting. So how does it differ from, for example, the current SOTA? I guess we will get it through the introduction a bit, like the context of how your method is different from the SOTA. How is it better? What's the
So
limitation?
surprisingly, the SOTA is literally you do data parallel. There is not that much
Okay,
innovation on it.
interesting.
There is a few modifications. Sometimes like you can look a lot, for example, DeepSeek paper did a lot of stuff to improve the distributed training, but all those new improvements are more like engineering method where you don't change the learning dynamics,
Hmm.
meaning you're also like quite bottlenecked by how much you can reduce this bandwidth problem. At some point, you need to change the learning dynamics, meaning that your model is not going to be the same. And that's what we're currently doing, where basically we are changing the learning dynamics. So I'm telling you that it's not a drop-in replacement. You will get different performance, but I'm telling you also that those performance are still good. That's the trade-off. And what's the SOTA? So everyone uses the parallel. However, our
Hmm.
method is very related to federated learning, which you could ask another SOTA. But unfortunately, federated learning has been I will say maybe corner in a specific setting, a lot related to privacy. So basically, when each device doesn't want to share information in between the others, and they have been focused on some peculiar small scale scenario where, for example, the optimizer is always HDD and everything, which is not
Hmm.
super representative and useful to train the large scale LLM. So I would say that DiLoCo is strongly based on federated learning, but with the modern twist of how to train large scale transformer.
Okay, can we elaborate a bit on the federate part of DiLoCo? Maybe go through I guess
Yeah,
the part two
absolutely.
with the algorithm, so to understand.
Yeah, let's zoom on the algorithm. So
Yes.
here, this is algorithm of FEDOPT DiLoCo. So that's not the one of this paper. It's like the one of a previous paper.
Hmm.
So I call it FEDOPT slash DiLoCo because they are roughly the same. There is some minor but quite critical difference. But to simplify, like FEDOPT is very representative generic algorithm of federated learning, where I said the data parallel you need to synchronize at every steps.
Hmm.
Here, FedOPT, DiLoCo, and a lot of federated learning methods, they synchronize only every 10 steps, 100 steps, etc. So they amortize the communication cost by synchronizing less often. So maybe, Ferdinand, can you zoom a bit on the algorithm?
For sure, for sure. Um,
Did you zoom? I don't see it zoom at all.
yeah, I think you didn't.
Okay.
All eyes on me different. Was
Okay,
the
okay.
turn
Oh,
left?
perfect. Yeah, I see it.
Okay,
Um,
nice.
the idea is that you have multiple replica. So each replica is an island of compute. So for example, a different data center. You have M
Mhm.
replica. You're gonna do multiple steps in parallel. So here, like that's the line two. So we do multiple steps from one to t, where we sample for each replica, they sample their data. So in line three, then in line four, they compute each of them respectively their loss with their parameters and their data.
Mhm.
And then in line five, they do some inner optimization step. So here, optimization step is whatever optimizer you want. In practice, unfortunately, a lot of the FedOPT and federated learning literature use SVD
Mhm.
because it can lead to more simple analysis and convergence. Here we use, in our case, in the local ADAM or any
Mhm.
modern variant because you need that to train a modern transformer. So here with multiple steps of Adam in parallel per replica. So they are not synchronized, meaning that each model diverge and the optimizer state is also separated.
Okay, so
And
maybe
then,
we
well,
can do like a small drawing. Maybe it's for like I would say like you start from this model, then everyone is
mhm,
diverging and doing like
mhm,
this. So you have at the end
exactly.
after okay, I just do another one. And after h equal, let's say, I don't know, h equal 500, then you do
Yeah,
something to synchronize back to the same model and you repeat the process, right?
yeah, absolutely. So with H being the number of steps every time we synchronize.
Okay. And so the federate part is here, I guess, when you average the weights.
The favorite part is like the whole thing that basically you have different model in parallel. So a federation of model, literally,
Okay.
that are only not tightly synchronized at the parallel, but loosely coupled together.
It's surprising that it works. Do you have like ideas why averaging model works in general? Like it seems magic a bit.
So there's two things. I will say that first, averaging doesn't work.
Ah, okay.
Or not enough. And then I will argue that also averaging works. So if you look at the souping literature, so souping literature is more like you take an existing pre-trained model, you
Hmm.
fork it into multiple model, you fine tune on different kind of data sets, different specialized, and then you merge them back and it works. And you can find a linear interpolation, making the best Pareto front between all the data sets. That's
Hmm.
something that we knew for quite a while with all the SWA and everything literature. But then Michael Warsman, more recently, with the model souping and everything, show that it just works very well and it's a very powerful feature. You see so many people on Hugging Face merging model and making them better.
Yeah, the
It seems
Frankenstein
that,
model, right? And
for
yeah,
example,
something.
yes,
Okay.
absolutely. And it seems to be working much better also at scale. So as you increase the scale of your model, probably because the model is more sparse and it's easier to merge them back together, it works
Hmm.
better. There was a paper, Task Arithmetic by Ilarco in 22, which show that basically as you get larger scale, and also another paper by Pratik Yadav, you do see the performance get better, and that's probably a feature that we only realize more recently. It's also even better with transformer, which is basically a huge matrix. While before when doing with the CNN, it was always a small convolutional filter,
Hmm.
which may also have been harder to merge.
Okay, interesting.
So that's why like merging like maybe work is like a lot of property of scale. You also need, as also a lot of paper from Alexandra May show, a common initialization to make it work. However, I will say that in this setting, merging doesn't work. So if you look like at line 6, so like basically every H step, so 500 for example, we do the synchronization. But we synchronize what? We don't synchronize the weights as you will do in merging. Otherwise, it's
Hmm.
not gonna work. So basically, in line 7, you compute a delta, so the theta, which is basically a delta in the parameter space between the weights of the replica. So the replica is the subscript m, the weight of the replica between in the past and now. So basically, your node on the top and one of the node in the middle.
Okay. So this one is the
And this,
reference, and then this one is the,
yeah,
I mean, T minus H on top and T, I guess, here. Oh, no, no,
yeah,
T and T minus H on top. I
yes,
guess it's
yes,
something like this. Okay. Then you
yeah,
do the
absolutely.
difference. Okay. And,
So,
oh, yeah, you just go on.
so the
Do the
question is
thing.
like, what is this? So the delta in the parameter space, there is different name. It's basically a trajectory, because it's like the trajectory you took for 500 steps of your model. You can also see it as a sum of update. So when I'm saying a sum of update is like the sum of all the update produced by the inner optimizer,
Hmm.
not the gradient, the update, importantly. And this thing, which is not a gradient, but we call it in our paper an outer gradients, and we act as if it was a gradient, and we're gonna synchronize that. So in line 8 and 9, we basically do a null reduce of that outer gradient for each replica, because you have one per replica, they have different trajectories. And then we say, oh, because it's like an outer gradient, it's like a gradient, we can optimize it. And we use an outer optimizer. And this is like
Okay.
something that was introduced originally in FedOPT, where they use as inner optimizer SGD, outer optimizer Adam. And this outer optimizer is critical. It's interesting if you look at outer optimizer and if your outer optimizer is SGD with learning weight equal 1, but basically you can just derive and you see that it's equivalent to merging the weights.
Okay.
However, merging the weights and SGD learning 1 is super bad.
I have one questions. Then it means that for DiLoCo, you have two optimizer. So in a sense, it's more memory intensive than data parallel, where you only have like one optimizer, no? I would say. Would
Yep,
you see?
that's so actually it's more than that. You have two optimizer, but you also have to keep a copy of the previous parameter. So the theta,
Okay.
t minus h. So it does add an overhead on the memory. The
Hmm.
good thing is that this thing, so the previous theta and the optimizer, is only required every H step. So
Okay.
for most of the time, you don't need it, and you can safely offload it on CPU and only reload it when you need it.
Okay. Okay. Interesting. So this was a presentation of the previous method. So what's the limitation?
Mhm.
What's justified the need of having a new method called streaming DiLoCo then?
I will go a bit on the left on the
Left? Okay,
contribution.
the contribution section, yeah. I mean
Yes.
the three contribution. It's
So just maybe
below.
to contextualize, so FedOPT is like inner optimizer SGD, outer optimizer Adam, and
Hmm.
some other peculiarity of federated learning, such as sampling of the worker. DiLoCo is inner optimizer Adam, outer optimizer Nesterov. We found that
Hmm.
Nesterov was just so much better to train large-scale transformer, surprisingly. And this is this kind of previous iteration. However, the problem is that we reduce the communication by amortizing. So we only communicate once in a while. But when we communicate, so at line 6 to 10, when we communicate, we do a blocking operation. We require a lot of bandwidth because we communicate the whole parameter tree.
Hmm.
And as communication is in full precision. So the question is like, can we, instead of doing amortization, can we smooth out the bandwidth usage across the whole duration of the training?
So just to be sure, when you say amortizing, you mean like with DiLoCo, every workers are waiting, right? For during the holidays. And now you want something where
Yeah.
a subset of them is waiting. That's
No.
the no?
What I mean is that right now, so we are when they communicate, they're all here. It's synchronous, so they're all synchronous, lockstep with each other.
Mm-hmm.
Yes, they are all waiting for each other. So first, you don't want to wait at all, and second of all, we amortizing because we don't communicate. We don't communicate. We communicate. We don't
Ah,
communicate. We don't communicate. So basically, you have a spike in your
okay.
bandwidth. What instead of having a spike, could you amortize it and like or make it more
Yeah,
smooth and having low bandwidth but quite continuous across the whole training?
it's not like a big or reduce. It's not a burst. It's like a small amount
Yes. Can we
every
avoid
time.
burst?
Okay, that's the
Absolutely.
amortize. Okay, makes sense now. Okay, thank you. Okay.
And so, but you can see on the left, the three contribution. The first one is like instead of synchronizing when we synchronize all the parameters, what if we synchronize once in a while a subset of the parameters? So that reduces
Mm.
the peak bandwidth. Then the
Subset.
second contribution.
Synchronized subset of parameter. Okay. Second is overlapping. Okay.
The second contribution is like instead of like doing like a blocking operation. So in practice, like I know in XLA, for example, in JAX, when you send an operation, basically you're gonna create a send node and a receive node. Right now, basically the receive node is a blocking operation. You want it absolutely, they're all coupled together and you're waiting for the communication to happen. What if we
Mhm.
can actually overlap? So you send the communication and then you keep, while the communication happen, you keep doing some computation step locally. So basically, this can increase the tolerance of the latency. Right now, like in data parallel or other methods like DiLoCo, you communicate and then you have to wait. Instead,
Okay.
and it's very sensitive to the latency of the communication. While if you could do computation, you don't care if there is latency because you can still doing work.
Mm. Okay.
And
Okay.
the third contribution is that also like instead of sending the outer gradients, so the only communication happening between workers in full precision, so usually it's either float 32,
What
but
the
more often in B float 16,
four
you
bits?
could send it in 4 bits. And if you can send it 4 bits, basically you are reducing by either 4 or by 8, depending on your original precision, the total amount of data exchange. So in total, your bandwidth can be 4 times lower.
So you're saying the auto gradient is in FP4 and it's
Yeah,
doesn't okay, this that's interesting. Maybe we could talk about this later. Like I
yeah.
don't see what justified the fact that before I mean float 40 I mean float FP4 it just works. It's crazy. But yeah,
We have some intuition about it.
okay, okay, nice. We'll talk about this later then. So maybe it'd be interesting to dive on the different contributions. So what's the next part of the paper? It's training part. So yeah,
Let's look
explaining
maybe
the
at the
algorithm.
line figure one, probably.
Figure
Figure one
one,
and figure two.
figure one, figure two, which are here. Nice.
Yeah.
Okay. Do you want me to zoom on figure one
No,
or
I think we can get like a bird view if the viewer can see well.
I think this is
So,
okay. Yeah.
okay, perfect. So DiLoCo, you do multiple local steps per worker in parallel. And then once in a
Mm-hmm.
while, you compute your outer gradient and you synchronize those. You do auto optimization and then you broadcast again.
Okay.
In streaming DiLoCo, we're gonna split our networks into multiple blocks. So here we explore like a very simple way where we consider that each block will be, for example, a whole transformer layer. So, for example, in a 1 billion chinchilla transformer, I think we have like 24 layers, but we can have like, for example, 24 blocks, let's say. So on the figure one, I'm showing a network where there is like 3 layers, the layers red, blue, and green. This is completely arbitrary for that figure. In the first iteration, we do multiple inner parallel optimization, so multiple steps. And then we choose to synchronize only the block red. So only one block instead of everyone. Then we do again multiple inner steps, and then we synchronize only the blue blocks. So first we synchronize only a subset of them, meaning that basically your model, each worker is never fully synchronized. Because when we synchronize, there's a subset of them that is the same value everywhere, but the other value are not the same. So it's quite interesting, and now you don't have a unique replica at any moment in time. You always have slightly diverging model.
Interesting. I feel like maybe it's out of topic, but this can be applied to other range of techniques. Like you can think of like a 3D distributed training, the classical with TensorFlow and stuff, and like
Mhm.
there's some constraint to make it correct, but you can like relax this thing in a way to, like for example, for TensorFlow, you could like add an optimizer somehow during the whole radius at each linear layer and just like relax the constraint and let that diverge, but that with this diversion you can like, I don't know, uh, maybe use TP across node, for example, because
Yeah.
this kind of thing. But,
I think the dream will be to make so this is distributed for data access. If you can
mhm.
distribute also the model access, that will be awesome. That's something we tried in another paper called DiPaco. It's much more sensitive
Ah,
to
okay,
here to
okay,
divergence.
okay,
If you do
interesting.
tensor parallelism, basically like here you're splitting your matrix multiplication across different devices. So then it's you have kind of like this expert sharding where each subset of the matrix could be seen as
Mm.
a individual expert. It can work with DiPaco, but it's much harder than this
Ah,
setting.
it's more harder to make conversion. Okay, interesting.
And I
So it's
think
good
that's a
to know
work
that.
that people should work on it because that's completely open research.
Interesting. Okay. Okay. And so I guess we see here that like there's like different way of streaming pattern. I
Yeah.
mean, how do you
So we didn't
synchronize?
explore like a lot of pattern. There's other people. So there was a paper published a few weeks after us called Dream DTPP, who did also something quite similar. They explore much more like the pattern. We can explore that more. I think there is little gain on it. We show on the figure two simple pattern we explored. So the one on the left would be like a sequential pattern. So here, for example, we choose to group two layers at a time and sequentially. So when we synchronize all the pair color. So first the color red for the embedding, then the color orange for layer one and two, and etc. There's this one. There's another one called the second cell, where basically it's always like color red, orange, yellow,
Yeah, so this
etc.
was
But
sequential.
here it's split apart, yeah. So it's threaded apart. We have some simulation that show first it will result in a slightly better compute utilization. We can overlap later a bit better the computation with the communication. And in our practice, it also gives slightly better performance. One intuition is that when we synchronize, but basically the synchronization is a bit spread apart the whole networks instead of located at a single location, which
Mm.
could be a helpful feature for the overall learning dynamics.
Okay, interesting. Okay, okay. So this is the trimming DiLoCo part. So the
Yeah.
overlapping.
So this is trying.
So so the synchronization contribution one is this. So instead of
Yeah.
synchronizing the whole model, you synchronize partition of it.
Yeah.
Then the second contribution is like overlapping. Overlapping comes from the streaming pattern, if I'm understanding
Uh,
correctly. No,
no,
or not
no.
yet.
The
Okay.
the string pattern is the synchronization. It's like what we synchronize, but
Okay.
it still means that if you could look, for example, at the figure one, for example, we only synchronize the layer red,
Ah,
but
yeah,
when we
you can
synchronize it,
continue
it's a
computation.
blocking operation right now. And how can
Yeah.
we make it not a blocking operation? So
Okay.
now I guess we need to look at the algorithm too.
Yeah, you can draw as well on the paper, I think,
Okay.
to guide if you want.
So in the yeah. So this so we have like the inner optimization that's as usual. So that's as before. We are symbolizing here a different subset of the parameters by, for example, if we look at here.
Wait,
So this, for example,
yeah.
theta MP, meaning like it's the parameters of the M replica, and it's for the fragment. So we fragment our networks into subset, fragment P. So now it means that we're gonna do multiple inner optimization for each replica. Then once in a while, here in line 6 to 8, we're gonna compute a subset, so the subset P, and we compute the outer gradient for that subset, so delta. And we're
Mhm.
gonna send the communication of that delta across to do a null reduce. So this is asynchronous. We send it in the background, and then we continue our work.
Okay.
And then
Okay.
the critical part, yeah.
You go on, go on, go on.
And the critical part is here, is after tau step. So tau is like how many steps we want to overlap compute with computation. After tau step, we block the reception of outer gradients. But in between time, we were still looping over the for loop, this one, where we're still doing multiple steps. And after two steps, we block the reception. So here it's a blocking operation. But by that time, after two steps, we expect that everything has been communicated and is already available locally. And we do our auto optimization.
Mhm.
Auto optimization, we only do it on the subset, so on that fragment outer gradient. And we only update that subset. Then the question is like, no, we have a new, for this subset P, we have a new fragment. However, this fragment P has been updated multiple times when doing here the inner optimization. So how do we combine that together that we know have like a fragment that was synchronized, another fragment that diverge? So we just merge them here. We explore two solutions, either one with alpha equals 0, where basically we replace the local fragment that was updated for two steps, we replace it with a synchronized one, or more simple, we do alpha equal 0.5, meaning that we merge uniformly equally the local fragment and the synchronized fragment. There is probably other way to find better alpha, as some people mentioned on Twitter, but for simplicity, we didn't push that too much. It
Okay.
also worked very well.
So mm, the alpha to me looks like a bit of an exponential moving average, or am I mistaken, or just like a normal average at this part? And
It's not really NMEA because NMEA that will be like sample the momentum of your optimizer. It's only updated with that NMEA here. It's a bit weird because you do a linear interpolation in between the
Mhm.
local unsynchronize and the global synchronize. But then after you do multiple afterward, you will do multiple steps to synchronize that inner. So that's not really an NMEA. Here I will say it's just like a linear interpolation between synchronize and local.
Okay, so if alpha is what's the, for example, if you put alpha equal to 0.8 or alpha 0.1, what's the
So
implication of
if alpha equals 0,
uh-huh.
um, well, I'm not very good to write. If alpha
Maybe
equals,
the stroke is too big.
yeah, I will let you maybe write. If alpha equals 0, you can
Uh-huh.
see that. So you have two replica. You
This
have
one was
this one on the left and this one, move your cursor, and this one on the right. The one on the right is the synchronized one with the tilde. So it's the
mm-hmm.
global synchronized one. The one on the left is the local, so different per worker, unsynchronized. If alpha equal 1, basically we're only taking the local one, meaning that we are not using the synchronization. So in practice, we have workers that are never synchronized, which is not what we want. It's equivalent. You could just have run like a local worker on a smaller batch size, and that's it.
Okay.
If alpha equals 0, that's the reverse case. We give all the importance to the global synchronize, and we discard effectively the local synchronize. So this means we wasted flops in a way for that local fragment. So it's just a fragment for two steps. In practice, it works quite well despite that, surprisingly. And we found best performance, especially with on two, the number of overlap is high, when alpha equals 0.5. So in between, you give as much importance to the local one to the global one. You could probably find a better way, maybe to dynamically through that alpha, but I don't think it will make so much difference compared to the already very good performance we have.
Okay. Okay. I have questions, but just in case we don't have Zoom Pro and in 5 minutes the meeting is ending, so maybe we'll do like a second meeting. And I didn't expect this
Perfect for
to
the
be
add-on.
like a 40 minutes of of um, of Zoom. So maybe we can stop now and I we can go back just after and then we'll cut in the. So yeah, so we were talking about the streaming DiLoCo algorithm. It's cool, but it seems like to be very useful at scale. But how do you, for example, verify this thing at small scale, for example? Like, how do you validate the thing?
So that's a good question. So as I said before, contrary to other methods like data parallel pipeline, here we change
Okay.
the learning dynamics. So first we need to be confident that I'm not going to error the model. So if I can
Uh-huh.
distribute my model, but the perfs are shit, you're not interested. So first, there's experiment. First, we're gonna do after like experiments on ML side, so that we prove our model is as good as data parallel. But first of all, I think I would like to talk more about how we show how much bandwidth we can gain. So all three contribution. So we synchronize once in a while a subset of parameters, we overlap the computation, and we do a quantize communication. Those three contribution, yeah, indeed. Um, those three contributions, so synchronization, oops, not the right cursor, sorry.
That's all.
The tree synchronization are basically more targeted to have a better bandwidth utilization. So the question is, how much are we winning? So for that, we built a simulator. So you should
Oh,
go to the
interesting.
section 3.1.
3.1. So I think it's
Um,
zoom a
or maybe
bit.
the
And
next,
then... Ah,
maybe
yeah,
the next
this one,
page,
this page.
rather. Yeah,
That's perfect.
yeah.
Oh,
So
okay. So,
first, let's look at the figure 3. So that was the simulator made by my coworker Yeni, who is co-author of this paper. Those figures are actually made with Matplotlib. I was very impressed he did that. So basically, with the simulator where we create some DAG, so directed
mhm,
acyclic graph, where we have multiple kind of node. We have the compute node and the communication node. In the compute node, we have in blue the forward node.
mhm,
We have in green the backward node with respect to the activation in light green and with respect to the weight in dark green. We have one of those nodes every time per layer of our transformer. Here we simplify and we consider all layers of the transformer the same. So it's only transformer block. We forget the boundary embedding. And we have the communication node in purple. So you can see that, for example, this row is data parallel. So in data
mhm,
parallel, I'm gonna do multiple steps here of forward. Oh, I made a big arrow. We do multiple forward for the whole layer. Then we compute the backward pass. And as we compute the backward pass with respect to the weights in dark green, we can launch the synchronization. So already data parallel safely, everyone does that. They already overlap a bit the computation with the communication. But
yeah.
basically, as you go back to your gradient, you can start the reduce at the same time. So that's cool. However, in practice, if you do decentralize, you will still have a blocking here, where here we are still doing some communication, and basically we are delaying the computation of the next steps. So in effect, during that time, like those, I don't know, here from like 0 to 25 seconds, there is not 0 to 25 seconds, but that's only fake numbers for that figure.
Mhm.
We are not doing computation. So that's wasted flops.
So this seems to be the same case for DiLoCo, right? So that's
So DiLoCo, yes and not, because like as you can see, data
yes.
parallel for the uh,
So
for
it's very blurry on my screen. I don't know if in the recording it will be blurry. So hopefully it's not. So either way,
it's good on my screen.
yeah, but hopefully it's a bit the okay. We'll see later. We probably a bit that it's not blurry. Because for me I don't
Otherwise,
see anything, so that's a bit annoying. But it's okay. We can continue.
otherwise I refer the reader to look at the figure 3 of the screen
Yes.
paper. In data parallel, you have to do this synchronization at every step. So at every step, you have this wasted computation. In
Uh-huh.
DiLoCo, we amortize. So the DiLoCo, the previous paper, FedOPT, etc., Fed learning, I show you. So here we are wasting communication at data parallel, but here there is no wasted communication because we are not synchronizing for that steps. We only synchronize
Mm.
once in a while. Here we synchronize every 2 steps. So already you can see that we amortize the communication, and data parallel is finishing later than DiLoCo because
Mm-hmm.
we were able to not do computation here.
Okay.
So that's DiLoCo. Streaming DiLoCo here is we're gonna do also synchronize once in a while. So we don't synchronize, for example, at this moment. But when we synchronize, we only synchronize here a subset of the layers. So instead of synchronizing here 4 layers as data parallel and DiLoCo, because here it's a 4-layer network, here we synchronize only 2 layers. So first of all, we were able, luckily, that this one was completely overlapped. This one is not overlapped, but it's only 1 layer. So we already reduce quite significantly the bandwidth and the time wasted in computation.
Mm. Okay,
Then
interesting. And
and
then
then we have, sorry, tell me.
I don't see the last figure because it's very blurry. So I guess the third one is like streaming DiLoCo, and the last one is streaming
with
DiLoCo
oh,
with
with
overlap.
computation overlapping. Yeah.
Okay.
And you can see that we communicate, but here we allow the gradient here to be overlapped. In practice, here like it's only a toy figure, so we overlap like a few forward node. But in practice, our overlap method, we saw it was dependent on the value tau of the algorithm. It's how many steps we overlap. So we could overlap multiple steps.
Uh, what? Et postérieur?
No, that's it. So we could have we could have overlap. We could have overlap multiple steps.
Mhm.
Sorry. We could have overlapped multiple steps, and basically the communication would have been like completely overlapped.
And
And
how much step can you overlap, for example, like
you
if
can overlap as much. So tau must be inferior to h. So basically,
Mhm.
you cannot have like a conflict where you are already trying to create the next outer gradients for the
Okay.
same fragment. But you can have like because it's multiple fragment, you can have multiple fragment of so the different fragment being in flight in parallel.
Okay.
Here, I'm not showing you like the third contribution, which is like quantizing the gradient, because basically it's just gonna make like the communication node, so the purple thing, just smaller. That's it. So it's not worth putting it in a figure.
Okay.
Um, and thanks to this simulator that we do, basically you can look at the whole duration of the training that will be done if there was no communication. So basically how long a training takes if we remove all the purple node. And we can look how long the training actually taking place when we take in account the communication node. So the length of the communication node is going to be dependent on the bandwidth. If you have a higher bandwidth, basically your purple node are going to be smaller. If you have lower bandwidth, they're going to be longer. And thanks to that, basically we can make a ratio that we call it a compute utilization, is how much
Mhm.
of your total time was spent doing computation instead of communication. And you don't, like GPU are very expensive. You don't want to pay like billions of dollars of GPU to do communication. So you want to maximize the computation time. So you want that number to be as high as possible.
Okay. And so just
And then
a
but you
quick,
can look at figure four. Yeah.
yeah, but before moving on to figure, so how do you build this simulator? It's like you simulate scenarios across like you took a node in the US and Europe and something like this. So it's just like
Yeah, it's just a DAG. So basically, like for data parallel, that how the nodes are
yeah,
going to
exact.
be, everything is deterministic. So you know how the nodes are going to be operated. You just unroll them, and then you see how long it takes.
Okay. Okay, fair.
So
Okay.
that's something that would be quite interesting for the open source community to reproduce it. I think it's quite straightforward. And here we can see basically three plots for 1B chinchilla model, a 10B chinchilla model, and a 100B chinchilla model. Their compute utilization for different variants. I think something that is quite critical to mention here is that we don't care about simply the bandwidth. What's also critical is the step time. If your model is spending a lot of time to do the step, so the forward backward before the
Mhm.
communication, basically you can get a larger compute utilization because in proportion you will have more time doing compute. So this is also a factor to take in account between the different model size. It's not simply the amount of data exchange.
Yeah, but for a small, I would say, model, you don't have, I mean, the computation doesn't take a lot of time, no? So it's
Yeah.
not,
Yeah. But for the small model, anyway, there is little data to be exchanged. So that's the
yeah,
thing that is awesome. So if you look here, maybe can you zoom bigger on one of those figures?
yeah, I'll try. I mean, for me, it's blurry, but for you, hopefully, it's not blurry. So the 1B, you want to check the
For
1B?
example, this is 1B. So on the x-axis, you see the one bandwidth. So basically, how
Mm-hmm.
much bandwidth in gigabit seconds we have between our worker. Here we simplify with two different workers. So for example, like Prime Intellect did with Intellect One, which was a reproduction of DiLoCo, you have one worker in the US, one worker in Europe, and a
Mm-hmm.
synchronize. So we have between 10 to the power minus one, so 100 megabytes, to 10 to the power 3, so 1 terabytes. If you have more bandwidth, your model will be much larger compute utilization, meaning they are doing much more time in computation than communication. So that's good. The question is like how much bandwidth you need to have good utilization. The data
So it's,
parallel here,
so it seems like data parallel needs a lot of bandwidth to maximize the compute.
Because data parallel here is very fast. So the 1B model, I think, is running in like in 0.2 second. So it do a full step in 0.2 second. So meaning that any time wasted is can be quickly multiple of your time doing a step.
Mm,
So also, the faster your model is, but the more you are potentially wasting computation.
okay.
It's proportional. So data parallel is like this. So it require, I think, up to maybe 100 gigabit seconds to be perfectly, or 200 gigabit seconds to be perfectly compute optimal in terms of pure compute utilization. Then in orange here, you see the vanilla DiLoCo, which communicate once in a while. In green, you see then the streaming DiLoCo that communicate once in a while a subset of it. So it's only slightly better because in total we communicate as much. It's just we can overlap a bit better, but we communicate as much data. And then in red, you have here like the streaming DiLoCo with overlapping compute. That's even a bit better because we can overlap with the compute. However, this thing is not interesting in that plot. It will be interesting in the other plots.
Mhm.
And in purple, we have the same one, but with overlap with FP4 computation.
Okay.
So something that is critical is, as said, each model have a different step time. And the longer your step time, which is usually the bigger your model, the longer your step time, the longer your step time, it means you also have more time to overlap computation. Because if you overlap, let's say, one step of computation, we can do more, but let's say there's only one step. Here, your model, a 1B model, is doing 0.2 seconds per step. The 10B model, I think, is doing like 1 second per step. And a 100B model is doing like something 20 seconds per step. Meaning that as you increase the model scale, you have more time to overlap computation.
Yeah, but if the hardware are different, and they're not different speed, like even if
I've,
you have
uh,
more time, like even if the H is the same, but they will take different time to reach the H, I would say, if I am clear.
I don't know some.
Like suppose you're training with two GPUs that are not as fast as each other, you will
We
synchronize the.
are, in that particular paper, we assume they all go to the same speed, each worker.
Okay, makes sense. Okay, so we see that at least for the trend seems to be similar for each scale, but I'm curious about like does it degrade
So,
the performance?
so I think like there's one thing that I think it's worth mentioning. I don't know if people have catch up. Is that you need more bandwidth as the model scale. So here, for data parallel, you need more bandwidth as a model scale because you just have more data to exchange.
Mm-hmm.
So that makes sense.
Yeah,
But
100, 200, okay. But
yeah,
it's
but
constant for DiLoCo. I mean, streaming.
with overlapping is almost constant because
Interesting.
or is sometimes even less bandwidth because sure you have more data to exchange, but because your step is also taking more time, you have more time to overlap it. So basically, those two effects counter each other. Bigger model, more data, but also longer steps, so more time to overlap.
Okay,
And that's the
interesting.
critical work that allows us to scale by quite well net on the networking for very large networks.
Interesting. Very interesting. But
Uh,
then again, it relies on the fact that you're doing floating point. I mean FP4, and assuming it's not
mm,
degrading.
so not even because like you can look at the in red that is like with the bfloat 16, which is how people communicate. It's
Yeah,
also
it's still constant as
almost
well.
constant.
Actually,
Uh,
yeah, it's
I
true.
guess more interesting if you can go to the last figure of the paper,
Let's figure out the
and then we can come back
paper.
to the ML result.
Those one. Ah, yeah, on
Yeah.
the llama, the llama.
Yes. So there is a llama, but also the DeepSeek that I think is more interesting.
Yeah, because the
Here
MO.
we DeepSeek is the MOE. So people say, sure, it's great because like it's only 35B activated. So you only activate 35B parameters per token. But MOE is always like much larger in practice because you have a lot of experts. Here, I think they have 128 experts, I think. So it's in total, it's like close to 700B total parameter to all reduce. And you can find here that when we overlap computation, so it's FP4. If it's a float before 16, it would have been maybe here, but it doesn't make much difference.
Mm-hmm.
We only require uh, a few like a few dozen of gigabits per second, while you will need like terabits per second. So it means that our method will scale even better for MOE, which gonna step a bit slower, and there are a huge amount of parameters.
Interesting. Okay. Okay. And
But again, those are only like the empirical or like this is simulated results on the bandwidth. The question, as I said, and as you remarked multiple times, is the ML performance okay?
so I think we can check on the evaluation side, I guess. So where is it, evaluation side? Just to
Uh,
understand. So I
no, this
think
is
yeah,
yeah, you can look here.
here is
Here,
yeah, there's a Hellaswagen result. Okay.
yeah, yeah. So we do experiments on two data sets, C4 and Dolma. C4 is a small data set, so it's a 200B token, but it's quite high quality, so it's nice to get quick results. We also do later experiments on Dolma, which is a larger data set, which a bit worse performance, I feel, per token, but because there's much more tokens, we can do a longer training. So first, we can just look on the figure 5, so A and B, where we do a chinchilla scaling law. So we scale a model from we scale models from like a small scale, so like 35 million parameters to 4 billion parameters. So it's a dense architecture, chinchilla. It's chinchilla compute optimal. So arguably for the current setting, it's a bit undertrained. You have in blue the data parallel, in orange DiLoCo, and in green and red streaming DiLoCo with overlap FP4 communication when we synchronize every 30 steps or 100 steps. So we cannot see very well on the figure, but we can look after, like there is a lot of table in appendix if people want the full results. But the conclusion is that basically on both the training loss and LSWAG accuracy, so one downstream eval, we find that our methods, both but the previous DiLoCo, but also our streaming DiLoCo, follow very well the parallel with basically the same loss roughly and the same LSWAG accuracy. And there is no sign that our model get worse as we scale, which is something that is often scary. It actually almost seems to get better as we scale, which is a finding we also find in model souping and everything. So we can also safely say that our model will scale well. Here we go to 4B, but for example, the Prime Intellect folks, they did
And okay.
DiLoCo, so not streaming DiLoCo, but DiLoCo up to 10B, and they also found good performance. So this is a method that really wants to scale.
But yeah, like if you were to scale even more, like 100B or something, do you have any ideas of potential issues that can come up that you didn't, or even at this scale, you can see some issues already that will very be present when you scale?
That's if you can know with certainty
I mean,
what will
some
break at a
hypothesis,
certain
I don't know.
scale, you should make your own lab and you will solve all the problem. That's a very big open problem. I
Hmm.
think you could scale a streaming DiLoCo to close to any scale. The biggest risk here is the float for communication that
Mm.
can be sometimes compression can break. So this will you never know. But at our scale, it works very well. Second of all, also is that in streaming DiLoCo, here we synchronize for every scale. We always synchronize 3 blocks at a time. I guess we should study more is like as the model get very big. So let's say you have 100 layer, 500 layer, 1000 layers. Maybe you should probably synchronize more layer at the same time,
Hmm.
and not just 3 layers. Otherwise, you will get too much desynchronized.
There's
Um,
something I wanted to talk about is like, I don't know where it is in the paper, but like there's a value equal to 5 and wait, this is
for the
only,
overlapping,
yes, yeah, it's
figure 8.
recommended to have like the overlapping set to 5. I think this here. Yeah.
Yeah, figure 8. So figure 8, so we look how much we can overlap steps. So basically that's the value tau in our algorithm,
Hmm.
if you remember. The more overlapping you can do, basically the less bandwidth you require. Of course, it's probably going to be worse to overlap too much. Um, we also discussed that there was a different value of alpha. So alpha equal 1 will be like we never synchronize, so it's not very interesting, so we didn't put it here. We have
Hmm.
alpha equals 0, where basically we are discarding the local optimization done for a fragment, which is wasted flops. an alpha equals 0.5, where we merge and give as much importance to the local fragment and the global synchronized gradient. You can find here on the y-axis the evaluation loss, so we want it to be as low as possible. And we find also in the x-axis the number of overlap steps. So the number of overlap steps, ideally, we would like it to be as high as possible to reduce maximally the bandwidth. We find that basically up to 5 steps of overlap, the loss is basically the same between no overlap at all, so 0, and
Mm-hmm.
5 overlap. For both the two methods, so both the discard method and the min, which is quite surprising. So you can waste in a way flops a bit for a little fragment, and that's not that impactful. However, as we scale the number of overlap to more like 10, 15, 20, you can find that if we discard here, like the number of flops wasted is too important, and that become like very detrimental, while our methods still get worse, but only gracefully. So that's why in our paper, we advocate that probably 5 step is a safe bet to not to go above with that current methods. We have a paper that was released after that where we can go to 100 steps and that works quite well, but that's another method. But basically, up to 5 steps, you get good performance.
And is there like a reason why going above is yielding this result? Like, what's the intention of behind it?
So if you do the discard method, it means that basically you're gonna do local optimization for like let's say 20 steps of your local fragment.
Mm-hmm.
So this local optimization is not completely wasted because they communicate with the other fragment, forward and backward, but still you are basically discarding the computation done for 20 steps for a fragment. So basically, if this fragment is 10% of your layer, basically, you are wasting 10% of 20 steps, which is relatively costly. So that's why this card is getting worse.
Mm-hmm.
Then for the mean, here it's a bit more complicated to interpret. It's going to be a trade-off between how much we wanted to get the synchronized version, which is a signal from more worker and more data, which is useful, but also how much we want to lose information from the local one, which in a way is wasted flops. So that's a trade-off in between. Here we do 0.5. Maybe you can find a better alpha. Maybe you can actually dynamically determine that alpha. But we didn't think that's something we wanted to push much more, given that 5 step is already enough.
Okay. Okay. It's made me think, do you have like any result that couldn't make it to the paper, but because of size or I don't know, but could be interesting as well to know?
If I have results, it's not in the paper, I wouldn't be able to talk about it.
Okay.
But
Okay.
we have a lot of results in DiLoCo in general. This work was more or less finished last year, and it's just a method that works, and we are keep working on it.
Okay. Okay. How to tell you're under NDA without telling you're under NDA. But okay. So I think I want to as well stress this weird point about like the FP4. Why is it working?
Hmm.
Like I don't know where's the
On the page on the one row under left,
yeah, yeah, here.
leftmost.
Yeah, yeah, here.
Yeah.
Okay. Oh, it's not blurry anymore now. Perfect.
Um,
So yeah, yeah, it seems like to compare different like compression algorithm,
mhm,
like
mhm.
pruning and stuff, and surprisingly, you have like the the low precision, the quantization, which is like almost perfect.
Yeah.
Bit weird.
Um, s- so, um, so here we show like the swag accuracy. So you want it to be maximized,
Uh-huh.
uh, and we show the evaluation loss that you want it to be minimized. You have also the compression factor that basically you would like to compress as much as possible to be on the left. So here we are considering the baseline is like using float 32 and you don't compress anything. Well, in practice, everyone communicate in bfloat 16 because bfloat 16 is not the default. Um,
So
we are comparing,
this is for the outer gradient, right? And the inner gradient is like
yes,
in float 32 or before 16.
in our gradient in bfloat 16.
Okay.
But that's what everyone does.
Yeah,
And
okay.
also, well, good point is like basically DiLoCo or some DiLoCo is just a new access. So basically, each worker in between can be made of multiple devices, and they can do data parallel, tensor parallel, pipeline parallel inside their local island of
Mm.
compute. So it's just a new access. And we explore like a different compression method. Arguably, we didn't explore super complicated method. Of course, there's a lot of literature, both in federated learning and in general data parallel, how to do other compression. Here, we choose to be quite simple. And we choose also like methods such as dropping values or top K and low precision, which are value also done by Cocktail SGD, which was a paper done a few years ago for gradient compression for data parallel. So I'm gonna maybe explain like each method what is it. So low precision, we instead of taking like a gradient of bfloat 16 with 16 bits or float 32 with 32 bits per neuron, we put it in a slower precision. We quantize it.
Hmm.
When you quantize, of course, by you're losing a range of values, which can be harmful. Fed dropout is a federated learning paper where basically we are randomly dropping value. So this dropout, we randomly drop value on our gradients with a certain probability of dropping them. There is similar, is more used in model merging, which is not exactly this current setting of outer gradient merging. But there is basically you do a dropout, but then you multiply by the inverse of the probability, the leftover neurons. So the in there is like you give more weights to the neuron that not have been dropped, which is similar actually how dropout works in inference for neural
Hmm.
networks. And top K is like you only keep the top
Top K gradient
K absolute values
value. Okay.
in your gradient. So per neuron, yeah. So we explore those methods. We see that basically dropout on there are equivalently very bad. So the loss get dramatically bad as we increase the dropout rate from 50%, 75%, and etc. We explore also top K, so 50%, 70%, and it's get quite worse as we get above probably 75%. But it's worth mentioning that you can do a top K of 50%. So you discard 50% of the value, and it's already pretty good. We explore each method individually. We didn't explore them combined with each other. So it would be interesting maybe to do, or if I do bfloat 16 and I do top K, for example, you could get the conjunction of 50%, 50%. Do we still get good performance or not? So that's
Yeah,
worth
but
exploring for future paper.
g given the graph, it seems like just using FP4 is like less hassle and directly better. So.
Absolutely. To scale large networks, there is already so much bell and whistle to do, and you never know if your stuff is gonna scale. So you want to be as simple as possible,
Mm.
use as little innovation as possible. So here we go from bfloat 16 to float 8 to float 4. So we use only 4 bits instead of 32 bits, and we
Hmm.
find barely any degradation. As you can see also here, maybe on the training loss, on the LSO accuracy, you can see that the performance change a little bit at bfloat 16 and FP8, and we are a little bit worse at FP4, but that's not very significant.
Is it like an average of experiments or just one experiment? Like,
It's one experiment. So all ablations are done at 500 M, so half a billion parameters on a normal setting.
okay. And do you have an explanation of why FP4 is not degrading, like an intuition at least, or hypothesis?
Yeah, so FP4, so first there's already been people doing FP4 on a gradient of data parallel. I think Cocktail SGD was doing something similar, maybe FP8, but it's a bit dangerous. Usually it works a bit worse. In our case, it worked quite well because we are doing the compression on the outer gradients, not
Hmm.
the gradients. The gradients are quite noisy because they are noisy with all the local batch, and your batch are sometimes like tokens that can make spikes or everything. The outer gradient is an accumulation of update across many steps. So here, basically, you can see it as a smooth trajectory that
Hmm.
remove also all the noise. And when you don't have any noise or much less noise in your value on your outer gradient, it's probably more amenable to be compressed.
Okay. So
That's
it
our
means that
general intuition.
okay, that at the outer gradient you have like not the best of the best, but like the clean version in a way. And that's why you can
Too
easily.
long.
Okay,
It's
interesting.
also something that other people have found concurrently at the same time. So while we are developing this, Prime Intellect released like their Intellect One model, so that 10B, and they also do FP for compression of the outer gradient. So here it's for DiLoCo, not streaming DiLoCo.
Hmm.
And they also found that it just works well, and they do it across the world. So it's a finding that as other people have confirmed.
Interesting. Okay. And is there any figures that we can go through? So we went quite a lot. Let me check where we went there. That this is the evaluations. Mm, I think we will
You
maybe
you
those
can maybe look at the figure 10, I guess.
10. So we went through already, no? I think
No, figure 8.
8. Oh yeah, we were just right.
Yeah.
Okay.
Figure 10 is like more like a open thing, but the intuition is like when we overlap compute. So I say like we are synchronized. So we have two workers, let's say, they're gonna send their outer gradient at the same moment in time. Then during the communication, they do multiple steps in parallel, and then they receive the gradient at the same moment in time. And
Hmm.
what if you wanted to break a bit that lockstep synchronization? So doing something async in between worker. So we did like some paper previously async DiLoCo that is very async. Here we are just a little bit where we have two workers that are gonna send the gradient at the same moment in time. They do the communication and they do multiple steps in parallel, but one of them is faster than the other. So one of them is gonna do 4 steps, for example, and the other only do 1 step. And then they receive the gradient. So they don't receive the communication at the same moment in time, and they are slightly desynchronized in
Offset.
time,
Yeah.
offset. How well our model will be. So here I'm showing you two things. So we are using alpha equals 0.25 for all. So the merging method. In orange, we have the previous orange line that you saw previously. The
Hmm.
y-axis is a bit different, so that's why it doesn't look the same. Where we basically uh, did I say something? Oh no, sorry, I made a mistake. Sorry. It's actually the blue line. The blue line is basically the blue line is equivalent to the orange line on the left. I'm sorry, where basically the two workers are doing overlapping of multiple steps, so
Okay.
from 0 to 20 steps. They do as much overlapping. While in the orange line, we choose what if the first worker only overlap 1 step and the second
Mhm.
worker overlap 0 to 20 steps. So they overlap different amount of steps, and we can find that basically we can still get pretty good performance. And we have, for example, one worker that did 20 overlapping steps, the other one did like 0 or 1 overlapping steps, and we see that in practice the loss didn't change significantly. So
Okay.
that's only a quick experiment, but that's a great step to also show that DiLoCo allow you to synchronize less often, reduce the bandwidth, etc.
But you
But can
can do it
also
async
help you
in.
to break the lockstep synchronization.
Mm. Okay. Okay. But still at I mean, what are the possible ways to make it more async, like compared to like the async DiLoCo paper? Like, can you bring some ideas from the async DiLoCo paper to this thing, or did
Yeah,
you try,
absolutely.
or but
No, we didn't try. That was not the scope. But the async DiLoCo paper, basically, we try different workers who have like a different speed.
mhm,
What we do is like a worker that is very slow is gonna synchronize more often the worker that is very fast.
mhm,
That's one thing. The second thing is we when they synchronize, they don't have we can update the auto optimizer. We can apply the auto optimizer for different workers, so not at the same time in time, but we update the momentum of the auto optimizer only once in a while by accumulating multiple outer gradient into a memory buffer. So it's a very simple solution found by our previous intern Bolio, and it just works very well.
okay,
So this will
okay.
be very extended. Streaming the local can be extended to do async as we did before.
Okay, so a lot of combination of method possible. So a lot of works. I don't know if there's a lot of people working in this area. Not sure. I'm not aware of. I know that this sending a small amount of data is very similar to what No Research was trying to do a bit, but differently, another approach, but instead of sending a burst, just sending a small fragment.
Yep.
Um, but yeah, so yeah, so maybe we're reaching the end of the paper. So what we can talk, I mean, about the limitation of streaming DiLoCo, then what's the next step after streaming DiLoCo, for example?
I think well, next steps could be our first to prove to people that they can scale to a very large size.
Mm-hmm.
Second, we should work on making it fully asynchronous between replica so that we really completely break and, for example, combine it with async DiLoCo to prove that this could work. And the third step will be also to scale easily the number of replica. So it's not transparent as you use two DiLoCo replica, four DiLoCo replica, etc. You don't get exactly the same performance. In practice, you will get a slightly lower performance as you increase the number of DiLoCo replica.
Mm, okay.
Uh, I don't think that's too much of a problem because you can combine, for example, in two different in doing DiLoCo replica between continent and inside the continent. You can, with the bandwidth is higher, you can do FSDP, DP, model parallelism, everything.
Yeah.
But it
So,
would be
so,
nice if we could show that we can scale it easily.
so if I understand correctly, it's like it's okay to have like different DiLoCo replicas, but you can compensate by having a lot of GPUs in one of their replicas. Like,
Yes,
yeah, it's okay.
it's
Okay.
in general all the local stuff is a new axis of parallelism that is
Mm-hmm.
combined with the other previous axes that exist.
Mm. And can you not do like a DiLoCo locally, and then like suppose you cannot go further than like five replicas, but you do a DiLoCo of DiLoCo. I don't know how to say that in a way. Like
Yeah,
this way you have like
hierarchical DiLoCo.
yeah, in a way.
That can be done. For example, there is like a Flower Lab. We do a lot of federated learning, and they have some stuff very similar to DiLoCo, basically with the same implementation. And they also did a paper recently called Photon, where they do hierarchical, where they have some kind of DiLoCo-like federated learning-like training
Hmm.
inside the region and in between region another level, so hierarchical. You can do that too. There is many way to solve this problem.
Okay, good to know that it's active. Okay, I think I'm pretty clear with the paper now. If you have, do you think that there is like other stuff that we should focus on more? I don't know.
I think we pretty much covered like the biggest point. Then again, there is like a lot of results, a lot of ablation, a lot of tables where we dump all the numbers. So I invite everyone to just have a look
Okay.
and read it.
Okay, so thank you very much, Arthur. And it was a
My
pleasure to
pleasure.
have, I mean, to better understand the paper now, and hopefully people will like it.
Thank you for inviting me.
Yeah, see you around. Bye.